Doesn't look like much of a costume. First of all, it's not Halloween, right? But this is the closest I could do. Second of all, it doesn't really look like a costume, but on the Zoom live stream, it'll kind of look like a costume. You might see what it is, but yeah, you guys can't see it in person. You also can't see it on the Zoom either, so sorry about that. But the costume is I'm going to be a floating head. There is no, this red, it will not be there, essentially. Okay. Oh, you heard, oh, okay, yeah, well, I'm not a lobster right now, yeah.
Was on the YouTube live stream?
Yeah. Well, like my body will, I mean, there's going to be an outline. It's not perfect, but with some special effects, I won't be visible. Anyway, so. Okay, so we're going to talk about integer linear programming. It's kind of the same thing as linear programming, except, well, in a few ways it's not. So recall like a standard kind of linear program. It's like an optimization problem of the form maximize C transpose X subject to AX is at most B, where like C is some fixed vector in Rn, A is a real m by n matrix, and B is a real a vector of length m. Thing is, I couldn't wear lobster claws because then I wouldn't be able to hold the chalk. It's already a little bit weird with this already, but. Okay, yeah, so if I wanted to add like integer linear program to this, it's basically the same thing. Well, it's going to appear to be kind of the same thing. You're again maximizing some linear function subject to some kind of linear constraints, but then you add another constraint that the variable has to take integer values. So this is like, so I add this kind of integer constraint. Okay. And that might seem like a very innocent thing to do, like just, okay, now I just allow integers. It might even seem to make the problem easier because, I mean, before my vector could be any real, vector. Integers seem kind of simpler, but actually this makes the problem much harder. So actually almost everything we've talked about in this whole course, so not quite everything, but almost everything we've talked about in the course, including like MP hard problems, can be reduced to solving an integer linear program. Right, because like, for example, yeah, if you wanted to compute like the size of a biggest stable set in a graph, you could just say, okay, I've got a variable for every vertex. For every edge, I need that the sum of those two variables is at most 1. And I'm going to set all my variables to be 0 or 1, right? And then maximize the size of the sum of all the variables. So in particular, solving. So yeah, also you could like for example, like the SAT problem, the stable set problem. What other example? Like 3 colorability problem for graphs. And most of the things we've talked about, they could all be reduced to solving an integer linear program. So therefore, since these are hard problems, solving an integer linear program is NP hard. Okay. So yeah, just adding this integer constraint makes the problem a lot harder. But here's the thing. I mean, we know that linear programs can be solved in polynomial time. So like, if I gave you an integer linear program, right, you could just kind of forget about the integer constraint, solve the linear program, and then like hope that it gave you a reasonable answer. So, I mean, that is kind of one approach. Is so the LP relaxation of an integer linear program is just the LP that you get by deleting the integer constraint. So if I just delete this constraint that said the variable x has integer coordinates or integer entries, then that would be the LP relaxation. Okay. So if I'm solving a maximization problem, so when I say the value of a integer linear program, I mean the actual like answer to the optimization problem. So I claim that there's some kind of relationship between these things. So the value of the integer linear program and the value of the LP relaxation. So it's either this way or that way. Can you see which way it's going to go? Which one's bigger? And specifically, I'm talking about a maximization problem. So if it's a minimization problem, it'll be like the opposite. So which one's bigger, the ILP or the LP? ILP is, yeah, the integer version. So it's going to be the LP because it's got fewer constraints. I mean, any solution to the integer linear program is also a solution to the linear program. So yeah, but there may be some solutions to this one that have a higher value, but that you can't reach with this one. So yeah, it's so the inequality goes that way, right? Okay. But suppose I gave you an integer linear program, and you deleted the integer constraint, right? You took the LP relaxation and solved it, right? And suppose so you solve the LP, and then you get a vector, like an optimal vector, right? I guess under what conditions would you be happy? yeah, if it just happened to also be an integer vector, then you'd be happy. So kind of a relevant question here is, under what conditions can you guarantee that the optimal vector for a linear program I'll say for the LP relaxation is integer valued. Right, because if there are some conditions where your LP is going to give you the right answer, that's quite important to know. I mean, that's quite useful to know, right? If I could, because it's hard to solve these things in general, but if somebody gives you an integer linear program with special properties, you know that you can just take the LP relaxation, solve it very quickly, and you got the right answer, right? So one condition that would be useful, so here's a kind of relevant question for this. So when can we guarantee that the vertices of the polytope polyhedron. It's not necessarily a polytope because it may not be bounded. P, which is the set of all x such that ax is at most b, are integer valued. Right? Because we know that, so this is a relevant question because we know that for every linear program, the optimum is attained at one of the vertices of the polyhedron that defines the constraints. So if all the vertices of this polyhedron have integer values, then it doesn't even matter what the objective function is. For any objective function, it'll be optimized by an integer vector. Okay. Okay. So yeah, if all of the vertices of the polyhedron are integer valued, we'd be very happy because we can literally solve for any objective function, any linear objective function, we can solve it on that polyhedron. Is that clear? Questions about that? Okay. Okay, so we're going to come up with a nice condition that will give us some integer vertices in a polytope, or polyhedron. I keep saying polytope, I mean a polyhedron. It may be unbounded. So the condition is going to be something related to the submatrices of a matrix, of the matrix A. So a submatrix of a matrix A is any matrix that you can get by deleting some rows and columns of A. Okay, so delete a bunch of rows, delete a bunch of columns. You've got a submatrix, right? So So this is the key definition. So matrix A is said to be totally unimodular which we're not going to write every time. We're just going to write TU. If all of its square submatrices so meaning like all of its k by k submatrices for every k have determinant -1, 0, or 1. So no matter how you delete rows and columns, if you come to a square matrix at the end and you compute its determinant, yeah, it's going to be -1, 0, or 1. I guess the unimodular thing is kind of like, I don't know if you, like 1, like it's like kind of like 1, like maybe, anyway, I guess a matrix of determinant 1 kind of, well, I don't know what this means, but it's something to do with 1s and -1s, right? Okay. Here's an observation. Well, maybe I'll ask you, like, what kind of entries can you have in a totally unimodular matrix? Like, could you have a 2 in there? Could you have any numbers you want? Well, and it's not meant to be a trick question or anything. Like, here's the thing. Like, a 1 by 1 submatrix is a submatrix. So each of your 1 by 1 matrices should have determinant -1, 0, or 1. But that just means each 1 by 1 like each entry is just a -1, a 0, or a 1. So every entry, because every entry is a 1 by 1 submatrix, so every entry is -1, 0, or 1 in a totally unimodular matrix. Because the entries are just the 1 by 1 submatrices. Okay, is this clear, or questions about that? Okay. Okay. Okay, so what's the relevance of this? So, well, the relevance is that these things give us polyhedra which have integer vertices. So, so if A, let's say, it's an M by N matrix, is totally unimodular, and B is an integer valued vector, then every vertex of the polyhedron P, which is the set of all x such that AX is at most B, is integer valued. Okay, so this is a nice thing because that tells you that if you have some integer linear program you're trying to solve, yeah, that's a hard problem in general. But if you just compute all these like determinants and you check and you realize, this thing's totally unimodular, then you can be like, screw the integer constraint, right? You just get rid of it, solve the system, solve the linear program, which can be done in polynomial time, and you just know that that's going to solve your original problem. So, okay. And we're going to see some applications of this as well. Okay, so here's the proof. So let A1 up to AM be the rows of M, or of A. Right, so like A looks like, so I'm treating all of these A's as like row vectors, so they're 1 by n vectors. Okay, and let Z be a vertex of the polytope, well, of the polyhedron of, maybe I should just say P. So that's a vertex of P. There was this thing we proved something about characterizing vertices of polyhedra a long time ago. I don't expect you to remember it, but I can just say it now. So what this means is that, so suppose I let AZ be the matrix you get by taking rows of A, which correspond to tight inequalities. So this is the matrix of all rows AI such that AI times Z, so Z is a column vector, AI is a row vector, so this multiplication makes sense, equals BI. So what we proved, this was a very long time ago now, but we proved that Z is a vertex of the polyhedron if and only if AZ has full rank, like it has rank n. So by an earlier result from chapter 2, AZ has rank n. I really hope I set up my computer correctly to take out this red. Otherwise, I'm just looking like a bit ridiculous. I mean, I'm looking ridiculous either way, but anyway. Okay, so this thing has it has rank n. It has, so A has n columns and m rows, right? This thing has rank n. I don't actually know how many rows this thing has. It might have some extra ones. But like I could always restrict now to, so it has n columns, it has at least n rows. I could just restrict to n rows that are linearly independent. So let AZ prime be a matrix consisting of n linearly independent rows of AZ. Okay, which must exist because the thing is, yeah, rank n. And then I'm going to let B prime be the vector coming from taking B and just including the entries corresponding to the rows that are in A prime of Z. So, so the vector obtained by restricting B to the entries corresponding to rows of A that are in AZ prime. Okay. I don't know if that's clear or not. Probably not. But my point is, like, AZ prime consists of some n rows from A. Some, I mean, I don't know which ones, but some n rows from A. And, right, so those rows each have a corresponding entry in the B vector. I just say B prime just takes those entries. So yeah, so B prime is going to be an integer vector of length n. Because AZ prime has n rows. So like this is also going to have n entries. Okay. And the point of this is that so you kind of think of what all of these tight inequalities, or these tight equalities, like what this corresponds to. When you kind of, so we're then restricting to A prime, but it's kind of the same thing, that like each row of Z, sorry, each row of A prime Z, let's say, times Z is equal to the corresponding entry of B. So yeah, we have this equality. And here's where the rank n comes into play. So since AZ prime has rank n, it's invertible. So it's like an n by n matrix with rank n. So yeah, it has an inverse AZ prime inverse. Essentially what I want to do is now multiply on the left side. Well, I will do that. So Z, so what I want to prove is that Z has integer entries. That's because it's the vertex of the polytope. And now I can solve for Z and write it like this. So Z is AZ prime inverse times B prime. Okay. Okay, now I need a little bit of, I need to argue that when I do this multiplication, it's going to produce integer values. Here's the thing. B prime has only integer values because B prime is like a sub-vector of B, and B had integer values, right? B was in Zm, B prime is in Zn. So I'm going to be happy if I know that all of the entries of this matrix have integer values, then I'm happy. Because it's just integers times integers plus integers when I do this, so it's going to be integer. Now this is something I don't really want to go through, but it does have integer values. So here are two facts that we know. We know that AZ prime has integer values, right? Actually, it only has ones, zeros, and negative ones. Like in that matrix, which are integers. Okay, and we know that the determinant of AZ prime, because it's a submatrix of A, so okay, technically the determinant could be -1, 0, or 1, but actually it can't be 0 because we already know it's invertible. So the determinant's either -1 or 1. because it can't actually be 0 because it's invertible. So now, maybe I won't like formally go through this, but it's true that if you have a matrix with integer values whose determinant is 1 or -1, the inverse always has integer values. So this implies that, or when I say hasn't, I mean has only integer values. So this implies that the inverse is integer valued. So these two properties. Okay. Quickly, sort of the rough reason is that, do you know, like, I don't know, doing some kind of a cofactor, you know, when you like compute the determinant and you go along the top row and you say, okay, this times the determinant of that and blah, 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 right? This times determinant of that. That's for computing the determinant of a matrix, but also by using these kind of submatrix, so which are called like cofactors or something. Cofactors are the determinants of these submatrices. You can use that to write an explicit formula for the inverse. And basically, all of these determinants are going to be 1 or -1 because these are submatrices of A. So these are a bunch of integer determinants. And they're also being multiplied by 1s and -1s. And then when you write down, so like the formula, basically the formula for the inverse, it's got like a 1 over the determinant of AZ prime times some matrix which turns out to definitely have integers in it. But this is a 1 or a -1, so that doesn't screw up the integer part. So anyway, so then, so this is integer valued. So therefore, I multiply an integer valued matrix by an integer vector. So Z is integer valued. Okay, so therefore every vertex of the polytope is integer valued. I said polytope again, but I still mean polyhedron. Any questions about that? Okay. So, okay, there is actually something I haven't really addressed here. I've actually been a little bit kind of wrong in what I'm saying. So sometimes you may have a polyhedron which has no vertices at all. That's a thing that happens, in which case, yeah, in which case this would be kind of useless because if there are no vertices, this doesn't tell you anything. But you can actually use this lemma to now get something that works for all polyhedra, even the ones without vertices. So, right, because, I mean, for example, how could I have a polyhedron with no vertices? Take three-dimensional space, take a hyperplane, take another two hyperplanes, and take all the things on like this side of that one and this side of that one. And basically, like these will intersect in a line, but there's no vertices in that polytope because it doesn't have any actual corners. So if we actually are interested in those kind of things as well, then we can also, well, let me just write what I mean and then I'll explain. So yeah, so note, not all polyhedra have vertices. I mean, they may be unbounded. But we can also deal with those things. So here's a definition. So polyhedron P, which is again X such that AX is at most B, is said to be integral if for all possible objective functions, the value of the LP, so where I'm maximizing C transpose X subject to AX is at most B, so is either infinity or an integer. Okay. Okay, so this is just being a little bit more general to also take into account the fact that, yeah, that you could have some unbounded polyhedra. You also want to be able to solve linear programs with those kinds of constraints. But of course, like if you have an unbounded polyhedra and you're maximizing along some line that goes to infinity, then it's infinity. But if it's bounded, you want it to always be an integer. Oh, I've messed that up because that's definitely going to have to be, it's got to be, it doesn't make any sense, right? It's got to be in Zn. I'll have to check that, but I think that's got to be in Z. Let's see what happens. Let's try to prove something and see what happens. So here's like a slight generalization of the last lemma. So if A is totally unimodular and B is in Zm, then the polyhedron X such that AX is at most B is integral. Okay. So suppose I take some suppose that this objective function is bounded above on P. Because, okay, if it's not, then it goes to infinity, and then I'm already happy because the value of this linear program would be infinity. I want to show that for every C, either I get an integer or I get infinity. If it's infinity, I get infinity. So we only have to consider the case where it's bounded. Okay. Yeah, I think this is going to be right, that I want these to be integer valued. So, so let X be an element of P such that, CTX is maximized, right, among all things in P. Okay. And yeah, this technically may not be a vertex of this polyhedron may not have vertices. It might be, like I'm saying, like kind of, imagine in 3 dimensions, you take everything on the side of this plane, and you have a straight line. Maybe this X is something on that straight line or something. Okay. But here's what I want to do now. I want to basically turn this into a bounded, like a problem where I do have, where I can apply the previous lemma. So let y and z be vectors, be integer vectors such that z is kind of sandwiched between y and z. So for example, you could just take every element, every entry of x and take the floor, take the ceiling. That could make my y and z, right? So now consider the linear program where what I'm going to do is maximize, again, CTX subject to AX is at most B. Also like so I'll write it as negative x is at most negative y, which just means the same thing as x is at least y. I just want to write the inequalities going the same way. And x is at most z. Okay. So I want to say that this thing has an integer, like the best possible, like the optimum of this thing is going to be an integer valued vector. Okay, so this x maybe is a different x than the other one, right? This is, maybe I should call this something like x star. And now I'm I've got a new variable x and I'm maximizing it. Now obviously the maximum of this thing is going to be the same as before, right? Because this LP could just pick x star, and then it's going to give the same value, right? I've realized that I can't see my watch very well, but so yeah, this LP has the same value as before because x star is a feasible point for it. But I claim that this one now is bounded, like. Well, yeah, I mean, it's obviously kind of bounded. I cannot take, like if I have some feasible point, like it's constrained between these vectors x and y. The solutions for this thing are stuck between two integer vectors. You can't just like go off in some direction infinitely, right? And I claim that these constraints are actually coming from a totally unimodular matrix. So I know that A is totally unimodular, but I've now got some new constraints, and I want to claim that those are also kind of, when I put them all together, I get a totally unimodular matrix. And then I'll be done, because we can apply the previous lemma. So this linear program is the same as saying kind of maximize CTX subject to, so I'm going to take a bigger matrix where I start with the matrix A. So these are like m rows and columns. I then take the negative of the identity matrix of the n by n identity. And then I take the usual identity, again, the n by n identity, but without the minus. And then I take x at most, the vector with the first m rows come from B, the next n come from y, negative y, and the next n come from z. Okay. So I'm just rewriting those constraints all in one big matrix. And here's the thing. So I'm not going to finish proving this because I think this is on one of your assignments. But this matrix is, so A is totally unimodular. And what I'm doing here is I'm just adding a bunch of rows where in each row that I add, like I add a row here, right? And then n of them. Each row that I add has just one -1 in one column, and the rest are 0. Or down here, each row here has 1, 1, and just zeros. So this is totally unimodular because it comes from a totally unimodular matrix by adding rows with only one, like plus or minus 1 value, and the rest, 0, basically. Like I just add, yeah. And you just do that like 2n times. And yeah, on your assignment, you'll prove that if I take a totally unimodular matrix and add such a row, it stays totally unimodular. OK, so therefore, this linear program is defined in terms of a totally unimodular matrix and an integer vector. And this is bounded because because of these constraints on x, like it can't just go off into infinity in any direction. So since it's a bounded one, this is actually optimized at a vertex of this polytope. And so anyway, so by the previous lemma, the max is attained when x is an integer vector. Okay, and then if x is an integer vector, then the maximum of this objective function is going to be an integer. Okay, so a little bit of thinking here to realize that this is, anyway, this thing defines a bounded polyhedron. So so then it's a polytope. So then the maximum is at a corner or a vertex. All the vertices are integer valued. Okay. So yeah, if you have any linear program where the constraint matrix is totally unimodular and the b vector is integer, it's got an integer value. Okay. Okay. Maybe I'll also say on top of this, so you can also often when we're doing linear programming, sometimes the constraints look like this, and sometimes they have a non-negativity constraint. So I guess maybe it's worth saying that the non-negativity constraint also can be incorporated into this. So if A is totally unimodular and B is in Zm, then the matrix P, where I take x such that Ax is at most B and x is non-negative, that's also going to be integral. Follows similar principles. Basically, this non-negativity constraint corresponds to just adding a bunch of rows to A, where there's exactly 1, 1 in each row, and so it's the same thing. Okay. Oh yeah, okay. There keeps being more things that I want to say. Yeah. a natural question is, how does this relate to the dual of the linear program? So, okay. So let A be TU and B, again, be an integer vector of length m. And now I'm going to let C also be an integer vector of length n. So suppose that a primal LP, which I'll write as, as usual, maximize CTX such that AX is at most B, X is at least 0, and its dual, which is minimize BTY subject to A transpose Y is at least C and Y is at least 0. So suppose that both of these are feasible. Okay. Then what I want to conclude, so then both the primal and the dual are optimized by integer vectors. Okay. So yeah, as long as both of these things are feasible, then they both have, and all these other conditions, then yeah, both of these should have optimal points that are integer valued. So this actually just applies what we just did and maybe weak duality or something. So like, yeah, since both of these are feasible, they both have finite value because I know that, so since the dual is feasible and the primal is at most the dual, weak duality, this can't go to infinity because it's bounded above by whatever that is. And also since the primal is feasible, then this is bounded below by whatever the primal is. So neither of them are giving me infinity or negative infinity. And then it just kind of boils down to, okay, A is totally unimodular, so this definitely has an integer solution. But then so does that one, because if A is totally unimodular, so is the transpose. So yeah, it's kind of the same. Okay. Let's see how this connects to other parts of the course. So I want to connect this to matchings. For this, I need to define the incidence matrix of a graph, which is kind of like the adjacency matrix, but not really, not quite. So let G be a graph with vertices V1 up to Vn and edges E1 up to Em. So the incidence matrix of G has n rows, m columns, where the where the kind of ij entry is 1 if vi is an endpoint of ej and 0 otherwise. I don't know, so yeah, so you've got a row for every vertex, a column for every edge. So if you think about it, if I look at a column, how many ones does it have in a column? Yeah, 2, because every edge has 2 endpoints. So right, all of these columns are pretty simple. Like it's mostly zeros, maybe, yeah, and then there's like exactly 2 ones, you know, somewhere. Right, and then if I think about any row, the number of ones corresponds to the degree of the vertex, right? Okay. Okay, so here's a fact about these incidence matrices, which I think, I mean, to me, it kind of makes Koenig's theorem make sense in a sort of broad context. Like this kind of explains to me why that theorem is true. So if G is bipartite, then, and this also kind of explains why maximum weight matchings in bipartite graphs, why all of that stuff is so much easier than in general graphs. So if G is bipartite, then the incidence matrix of G is totally unimodular. Okay. And the thing is, if you were trying to find the biggest matching in a bipartite graph with a linear program, like this is the matrix you would use to make the constraints. Like you would, because every vertex you would have to have, yeah, I would have like a variable for what, every edge. Okay, maybe this should be the other way around or something. It doesn't matter. I'd have a variable for every edge, which is like between 0 and 1. Every vertex, the sum of the variables of its edges should be at most 1, and stuff like that. This would be the right constraint matrix. If this is totally unimodular, then that explains why the dual of that linear program, which computes the vertex cover, like why these things always give the right, the same answer and stuff. Anyway, let's prove that this thing is totally unimodular. So consider, so what do we have to prove? We need to prove every square submatrix has determinant 1, -1, or 0. So consider a square submatrix, like a k by k, let's say, submatrix of the incidence matrix. Okay. Let's call it A. Okay, I want to show A has determinant 0, -1, or 1. Okay. I'm going to break this into a few cases. the good thing about this matrix is not that complicated because, I mean, like we said, every column of the incidence matrix, it's only got 2 1s in it, right? That's somehow going to make our life easy. So let's say case 1, A has a column with no 1s. It's just all zeros. Okay. In that case, I'm pretty happy. So, yeah. So A, by the way, it's a submatrix. So it's like it's obtained by choosing some rows and columns, right? Suppose I chose that column, which I've just like erased with my long fingers here. But if I chose that column, but I didn't choose those 2 rows, then I would get a column of zeros, right? So that could happen. But like this is a silly case because then, I mean, the determinant's just 0. So case 2, A has a column with exactly 1 1. I guess I should have said at the beginning, I'll do this by induction on K. The case K equals 1 is easy because every entry is a 0 or a 1, right? So let's say K is bigger than 1. Okay, I want to compute the determinant of this thing. Can anyone see if it had a column with exactly 1 1, how would that help me? Actually, the idea here is going to be helpful on your assignment. It's like you do that, like, oh yeah, yeah.
If there's only 1 1, then you would only really want to do
Yeah, if you do that like cofactor thing or Kramer's rule or whatever you call it, I don't know, but you're right. If there's some column with 1 1 in it, you could kind of like go down that, like this way you compute the determinant, you could go down that column. Exactly, and then you take this times some subdeterminant, but that's 0 times something, I don't care. Like this is what when you're in linear algebra class, right? When you learn this trick, like you pick a row that has or a column with a lot of zeros because that's going to be easier, right? So anyway, yeah, so I'm getting 0 0, and then finally I get one thing with a 1. So I'm computing the, what am I drawing here? The determinant of like this thing times a 1, but like this thing by induction has determinant 0, 1, or negative 1 by induction. So, and I'm multiplying by 1. So yeah. So then, I don't know, is it called Kramer's rule or whatever it's called? I mean, compute the determinant by going down that column. And use induction on K to say that this K minus 1 by K minus 1 thing has the right determinant. So yeah, and this may multiply by a negative 1 depending on the parity, like if it's the second or third or whatever. But yeah. Okay, case 3 is that all columns have 2 1s. Okay. So basically this is like, yeah, we've picked some edges and we've picked all the vertices that are involved in those edges. So we've picked a subgraph, basically, like essentially. So far, we haven't used anything about being bipartite. So this somehow has to do with bipartiteness. So imagine you take like the graph that you get from like the edges you've selected to be in this matrix. Okay. Okay, I claim that the determinant's going to be 0. Can anyone see a reason? So let's say I've selected the columns corresponding to these edges and the rows corresponding to these vertices, like in this picture. There may be more graph outside, but anyway. Or you may as well just think of the whole graph, basically, right? Why is the whole determinant at 0? Here's the trick. Every edge includes a vertex from this side and from this side. Take the rows corresponding to the vertices on the left, sum them, sum those rows. That'll count every edge once. So that's going to give me a vector that's like, yeah, that'll give me like the all ones vector, because every edge has one. So I sum over the rows corresponding to these vertices. And yeah, every edge is kind of counted once. So everything it'll be an all ones vector. Sum over these ones, it's also the all ones vector. But I took two different sets of rows that both sum to the same thing. That's a linear dependency, because if I subtract those things, I'll get 0. So yeah, so summing over rows corresponding to vertices on the left side counts every edge once. So it gives me the all ones vector. But that's the same as for vertices on the right side. So when I say left side, I mean of the bipartite graph. So the rows are linearly dependent. Okay, so then the determinant of this submatrix must be 0. Okay. So yeah, if I can make the all ones vector in two different ways, because I am summing different, I'm summing completely disjoint sets of rows here, the ones on the left and the ones on the right. I made the all ones vector in two ways, subtract them, you get 0. And yeah. Okay. Anyway, this idea of doing this whatever Kramer cofactor expansion, whatever it is kind of a good idea for showing things are totally unimodular. Okay. Okay, so we're almost done, but maybe I'll just say that if you combine all of these things that we've done today, this gives you another proof of Koenig's theorem. And there's going to be more, don't worry. It's not the last proof of Koenig's theorem we're going to see. But yeah, because basically if you write down the linear program for computing the largest fractional matching, that has a totally unimodular constraint matrix. So it's optimized by an integer vector, which is just a matching. And then the dual also has by this theorem that I just said, it's also optimized by an integer vector, which will be a vertex cover. So it also gives you like a stronger version of this, of Egger-Vari's theorem. This is a thing that came up at some point. I think I probably only stated this once, but yeah, so suppose each edge of a bipartite graph has an integer weight So if I add this kind of constraint that all the weights are integers, then the max weight of a matching is equal to I didn't write this down, so I feel like I'm going to mess it up, but the minimum of the sum of f of v over v in the vertex set over all functions f from the vertex set to the integers. Well, actually, no, I want to say to the non-negative integers. So let's, I don't know, natural numbers union 0, such that f of u plus f of v is at least the weight of uv for all edges uv. So, okay, E here is the edge set of whatever graph. I didn't even name the graph, but. So we did have a theorem like this before. Yeah, this Egger-Vari's theorem, but there was a difference. So the difference is before I just let the weights be anything, but then the function was just mapping to like the 0 to infinity. So we didn't have any guarantee that, like in any case, we didn't have any guarantee that the function would have integer values. But now what I'm saying is that if the weights are integer on the edges, then you can make your function integer on the vertices. So it's kind of, and that kind of corresponds to, suppose the weights were 1, then what we're looking for is a biggest matching. Then this function is going to be, it's also going to be integer, which corresponds to a vertex cover. Like, because if I put, let's say 0, 1 values on the vertices, it's going to correspond to a vertex cover. Okay, anyway, that's, all of this follows from this totally unimodular stuff. Any questions about that? Okay, so then, yeah, we're jumping to a lot of different topics. We'll do something new next time.